Hello my dear friends, welcome back again to our YouTube channel Invisible Threads. Hope all of you are doing well in this difficult period of time. So I hope you have followed my previous video on numericals, mostly on electric potential and the electric potential energy. So today in this video I will discuss some more numericals for the interested students for a better and clear understanding of the concept. Hope this discussion will be very helpful. So let's begin. So I will discuss about some advanced numericals on electric potential and the potential energy. So our first problem states like a small spherical pith ball of radius 0.5 centimeter is painted with a silver paint and then minus 10 microcoulomb of charge is placed on it. You can see this is the small spherical pith ball of radius 0.5 centimeter. I am indicating here, having the radius of 0.5 centimeter, and over the whole sphere it is minus 10 microcoulomb of charge is there, and the charged pith ball is put at the center of a gold spherical shell of inner radius 2 centimeter and the outer radius is 2.2 centimeter. So this is the spherical shell of inner radius 2 centimeter and the outer radius is 2.2 centimeter. You can see this is marked here. So now I need to find the electric potential of the gold shell taking the zero potential at the infinite distance, and also how much charge should you put on the gold shell if you want to make its potential is 100 volt. So this is the two questions I need to answer. So you can see this, the radius of the pith ball is 0.5 centimeter. So 0.5 centimeter means 0.005 meter. The charge on the pith ball is minus 10 times 10 to the minus 6 coulomb. It means minus 10 microcoulomb. Now the inner radius of the cell is 0.02 meter and the outer radius of the cell is 0.022 meter. So as we all know that the electric force constant is K is equal to 1 by 4 pi epsilon naught is equal to 9 times 10 to the 9 Newton meter square per coulomb square. So for the question number 1, find the electric potential of the gold shell taking the zero potential at the infinite distance. So you can see that if we try to bring the charge, the pith ball is here, it is placed inside the gold shell. So now initially I need to calculate the potential of the shell. So if we try to bring the pith ball which is inside of the spherical shell, so from the infinity to the center of the spherical shell, the work needs to be done and the work will get converted to the potential energy of the shell. So this is the physics. So you can see I need to calculate the work done. So this is the V means minus of E dot dl from the lower limit to the upper limit. So I will break the limit in two parts. One is from minus infinity, one is from infinity to the distance of 0.022 meter. It means at the upper surface of the spherical shell, and the another part will be from the upper surface of the spherical shell to the center of the spherical shell, means minus 0.02220 E dot dl. So but you can see that the inside the spherical shell, I have discussed before, the electric field is 0. So only this part will exist. It means infinity to minus of infinity to 0.022 kq by r square time r cap dot r cap dr. It means the electric field for the spherical shell where the charge is inside. So the electric field, what it will be, kq by r square. So where is the q is the total charge of the spherical shell. So it means because, and the second part will get 0 because the electric field is 0 inside the shell. So you can see that it comes out to be that minus kq of lower limit infinity to 0.022 1 by r square dr. If I integrate and put the limit, I will get the value of the potential is equal to minus of 4.1 times 10 to the 6 volt. So this is the potential of this spherical shell if I put the pith ball inside the center of the spherical shell. So for the second part, you can see that again the net charge on the shell I need to make the potential of the spherical shell of 100 volt. So suppose I need to find the net charge. For that, the potential of the spherical shell must be 100 volt. So V is equal to kq net divided by r. This is the potential expression for a single point charge, as we all know. So I need to find the q net at first. So q net, what it will be, Vr divided by k. So it comes out to be 0.022 times 100. This is the voltage, this is the R is 0.022, the outer radius of the spherical shell, times the voltage, the final voltage I need, it is 100 volt, divided by K, it means 9 into 10 to the power 9. So it comes out to be the Q net is equal to 2.4 times 10 to the minus 10 coulomb. Now you can see this is the at the surface of the spherical shell. To get the potential of at the surface of the spherical shell 100 volt, I need the net charge of 2.4 times 10 to the minus 10 coulomb. But as the pith ball is inside the shell, induced charge on the inner surface will be 10 microcoulomb, because I have discussed in my previous video that if I put some charge inside in the inner surface of the cell, will get oppositely charged. So here on the pith ball there is minus 10 coulomb. So you can see in the inner surface of the spherical shell there will be plus 10 coulomb, and to make the spherical shell as a neutral one, for the upper surface of the another surface of the spherical shell, it will be minus 10 coulomb. So here it will be minus 10 again, minus 10 microcoulomb. So as the pith ball is inside the cell, induced charge on the inner surface of the cell is 10 microcoulomb, and for the outer surface it will be minus 10 microcoulomb. So this is the Q sphere. So on the upper surface of the spherical shell there is Q sphere charge is already there, but I need the amount of charge is 2.4 times 10 to the minus 10. This is the net charge. So how much additional charge I need to put on the spherical shell? So the additional charge needs to be put on the spherical shell will be Q is equal to Q net minus Q sphere. What it will be like 2.4 times 10 to the minus 10 minus of minus 10 microcoulomb. So it comes out to be around 10 to the minus 5 coulomb. So this is the additional charge I need to put on the spherical shell to get the potential of 100 volt on the surface of the spherical shell. So our next problem will be like, calculate the angular velocity omega of an electron orbiting a proton in hydrogen atom. The radius of the orbit is 0.53 times 10 to the minus 10 meter. You may assume that the proton is stationary and the centered centripetal force is supplied by the Coulomb attraction. So this is the data as we all know that the electron charge has 1.602 times 10 to the minus 10 coulomb. Mass of the electron is 9.11 times 10 to the minus 31 kg. The Bohr radius is 0.53 times 10 to the minus 10 meter. This is the first orbital radius. And the electric force constant K is equal to 9 into 10 to the 9 Newton meter square per coulomb square. So you can see that in hydrogen atom one proton is there in the nucleus and the one single electron is revolving around the nucleus. So the electric force on the electron and the nucleus, what it will be, F electric, K Q1 Q2 divided by R square. Here Q1 and Q2 both have the charge of the same, so it comes out to be K Q square by R square, because in the nucleus there is one single proton and outside in the orbit there is one single electron is revolving around the nucleus. And the centripetal force also on electron, what it will be, Fc is equal to mv square by R or m omega square R, by putting V is equal to omega R. V is equal to omega R. So from there we get the value, we get the relation that the centripetal force is m omega square R. So there must be a balance in between the two forces. One is the electrical force, another one is the centripetal force. So we can get that the centripetal force must supply the electric force. So F electric is equal to F centripetal. So after equating both the forces, what we can get, K Q square by R square is equal to m omega square R. So omega has a value of K Q square divided by m R cube whole to the power half. So if we put the value of all the quantities, like K is equal to 9 into 10 to the 9, Q has the charge of the electron or the proton, you can say, only the magnitude we are considering. So Q has a value of 1.6 times 10 to the minus 19 coulomb. M mass of the electron, what it will be, 9.11 times 10 to the minus 31 kg. I am putting all the values in MKS or SI unit. And the first orbital radius is 0.53 times 10 to the minus 10, its whole cube. So the omega comes out to be 4.12 times 10 to the 16 radian per second. So omega has the unit of the angular velocity, has the unit of radian per second. So this is the value of the omega. So our next problem will be like, if the Coulomb's law involved 1 by r cube dependence instead of 1 by r square, as we all know, for the point charges, the force in between the 2 point charges depends on 1 by r square. Would Gauss's law be still true? I need to show if there is a still validity of the Gauss's law. So from the Gauss's law, as we all know, that the closed surface integral of E dot ds depends only on the charge enclosed divided by epsilon naught. So this is the closed surface integral So this is the amount of the flux coming out from a closed surface is proportional to the Q enclosed, only the charge enclosed by the surface, the Gaussian surface. Now the electric field involves 1 by r square dependence, as we all know, and the area vector involves r square. So this electric field is proportional to 1 by r square and this area vector is proportional to r square. So therefore the product becomes constant because it does not depend on r. So only the enclosed charge, it will depend only on the enclosed charge, because 1 by r square times r square, it becomes a constant. But if the Coulomb's law has 1 by r cube dependence, you can see, then the product of the electric field, which is proportional to 1 by r cube, and the area vector is similarly like before, it will be r square. So the 1 by r cube times r square, it means there will be a 1 by r dependence. So it is not independent of r. So finally it depends on r. So then the Gauss's law will not be true, because there will be r dependence, and because there will be r dependence, so the right hand side will not be a constant one, so it will depend on r. So we can say that if the Coulomb's law involved some 1 by r cube dependence, so the Gauss's law is not true in this case. So our next problem will be like, so you can see in the following figure, it is mentioned, it is diagram here, I have drawn the figure here. In the following figure, it shows a charge array known as electric quadrupole. So quadrupole means 4 charges are there, Q, minus Q, minus Q and Q. In between Q and minus Q, the separation is A. In between minus Q and Q, the separation is also A. And this minus Q and minus Q both are located at the same point, which is Y. It means at the point Y there is minus 2Q charges. For a point on the axis of the quadrupole, obtain the dependence of the potential. So for a point on the axis of the quadrupole, suppose at the point P, I need to calculate the potential. So it means I need to, at the point P, I need to calculate the V, which is a function of the R. So compare your results with that of an electric dipole and electric monopole. Monopole means single charge. So you can see this is the quadrupole configuration I have drawn here. This is the Q, this is minus Q, and at the same point again there is minus Q1 and this is plus Q. So from the center of the quadrupole at a distance of R, at the point P, I need to calculate the electric potential. So from the figure you can see the XP is equal to R plus A from the figure, YP is equal to R, and the ZP has the distance of R minus A. Now it can be considered that the quadrupole has 3 charges. What are the 3 charges? One is Q, minus 2Q, and again Q. You can see. So electric potential for these three charges at the point of P, how can we find? That V is equal to 1 by 4 pi epsilon naught. All are the point charges. So for this charge the distance is R plus A. So it comes out to be V is equal to 1 by 4 pi epsilon naught times Q by R plus A minus twice Q by R plus Q by R minus A. The 3 different charges has 3 different distances. So it comes out to be Q by 4 pi epsilon naught 2a square divided by R times R square minus a square. So it comes out to be 2qa square divided by 4 pi epsilon naught R cube times 1 minus a square by R square. Now I assume that the distance in between the Q or minus Q or minus Q or Q, the distance is A, which is very less than R, this distance R. So from this consideration we can get that A by R very less than 1. So a square by R square, this term we can neglect. So V quadruple comes out to be 2q a square divided by 4 pi epsilon naught R cube. So for the quadruple it depends on 1 by R cube. Previously I have also discussed that for the dipole it depends on 1 by R square, and for the monopole or for the single charge it depends on 1 by R. So you can see for the monopole it is 1 by R, for dipole it is 1 by R square, and for the quadrupole it varies as 1 by R cube. So different charge configuration, the potential we can get different potentials. So for the next problem, number 5, 2 charge conducting sphere of radii A and B are connected to each other by a wire. So you can see this is the 2 different charge sphere A and B of radius of small a and small b, and this one has the charge of Q1 and the surface charge density sigma 1. This one has the total charge Q2 and the surface charge density of sigma 2. So you can see that we can write, so I need to find what is the ratio of the electric field at the surfaces of the 2 spheres. I need to find the ratio of the electric field for both the sphere A and B at their surface. Use the result obtained to explain why the charge density on the sharp and pointed ends of a conductor is higher than on its flatter portions. So for a conductor where there is some sharp end, the charge density there is higher rather than a flat portion. I need to prove it. So we'll discuss, our discuss will begin like, for the V1, for the charge for the sphere A, the potential at the surface will be V1 is equal to Q1 divided by 4 pi epsilon naught A. For the sphere B, capital B, having the radii of B, small b, the potential at the surface will be V2 is equal to Q2 divided by 4 pi epsilon naught B. So both the spheres are connected by the wire. So till the potential of the two conductors become equal, the flow of the charge continues, because until the potential of the two spheres are become equal, the charge will flow from the higher potential to the lower potential. So at equilibrium we can write that V1 is equal to V2. So after equating these two, we can get the relation Q1 by Q2 is equal to A by B. So again, electric field on the surface A, on the sphere A, what it will be like, E1 is equal to Q1 divided by 4 pi epsilon naught A square. And electric field on the surface of sphere B, what it will be, E2 is equal to Q2 divided by 4 pi epsilon naught B square. So I need to find the ratio of the E1 by E2. It comes out to be Q1 by Q2 times B square by A square. So it means I put the value of Q1 by Q2 A by B here. So you can see A by B times B square by A square is equal to B by A. So the ratio of the electric field is inversely proportional to the radius of the spheres. You can see. Similarly, the charge density of the sphere A, sigma 1 is equal to Q1. The total charge is distributed evenly on the surface of the sphere. Q1 divided by its surface area, it means 4 pi A square. Similarly, the charge density of B, sphere B, sigma 2 is equal to Q2 divided by 4 pi B square. So I need to find the sigma 1 by sigma 2. It means Q1 by Q2 times B square by A square. It means I put the value of Q1 by Q2 as A by B times B square by A square. So it comes out to be B by A. So you can also see, like electric field as before, the charge density also varies as 1 by radius. It inversely proportional to the radius. So now for the sharp end of a conductor, we can assume that the radius is very small for some sharp end and sigma is more. It means, because if the radius is small, the sigma gets higher. So the charge density, the charge will accumulate at the sharp end. And for the flatter portion, the radius is large, because for the flat portion we can assume that it has the radius of curvature of very large, so sigma gets lower. So suppose this is the sharp end, so you can see from the diagram the charge will get accumulated here, and for the flatter one there will be no accumulation of the charges. It will be evenly distributed. And this is the flat surface and this is the sharp end. So my friends, I am concluding my discussion here. If you have any kind of question and facing up any kind of difficulties, don't hesitate to let me know in this video's comment section. Stay tuned and keep supporting Invisible Threads. And please do like, share and subscribe our channel as much as possible with your family and friends. Stay safe and thank you.